first, is a commutative finite-dimensional algebra. We can regard it as a Cardan subalgebra.
Uh-huh.
And M is a module over H. It's just a representation of and mean a weak decomposition. And we should prove that any submodule of this M admits a weight decomposition. It means the weight will coincide with the weight in M.
Mm-hmm.
And according to the hint, we should prove that first we choose some weight vector in M. There exists some element A1, AK in UH such that. Okay, so first we consider this was this. Since this is the universal enveloping algebra, but our Lie algebra is H is commutative, so this is just the polynomial. Let's first suppose that the base of this finite dimensional algebra is H1, Hn. So
yes.
This is the polynomial. This is just this. So what we have some. According to these, we have H I
Mm-hmm.
Bg. Bg comes from here. This equal to num G.
In less invariant, so let me just comment. So in less invariant terms, this is also what you try to say here is that it is also like S of H, right? Symmetric.
Yeah.
Which is a polynomials on H star, right? But yes, explicitly you fix a basis, and in this basis just polynomials. Mm-hmm.
We have this. This we can regard this is also a monomial of degree 1, and
Mm-hmm.
we should find some polynomial this such that this happened. And
Okay.
This is we can use the Lagrange polynomial to find such a polynomial.
Yes. So Lagrange interpolation is usually for one variable, right? But for many variables there is also such
Yes.
similar thing. Yes.
Okay, this is a polynomial.
A lot of technology is used in this seminar.
For example, we should find K polynomial, and now we just consider one. We can say we consider V1 case. We should find such a thing that find such an A1. Now we try to find A1.
Mm-hmm.
Such A1 B. What we do this is you can write down the explicit formula of these things.
J.
Which one? One. Oh, so I is one. No.
If you remember.
So you're writing A1 explicitly. Okay,
Yeah, yeah.
yes, very good.
That is the algebra.
Very good, very good. So let us check at least. So if I have j equals 1, right?
Yeah.
Then I should have A1 acting on V1 is V1, right?
Yeah.
Let me, can you do it
Oh,
just to check?
A1 acts on V1. And this is some constant. And just
Right.
this is a constant and also give so we have only H1 act on V1 and also some act on V1. So and H1 act on V1 is none of one. H1. Good.
Yes.
And so the things we have is none of one. H1 minus none of one. H0.
Uh-huh.
H1.
Okay.
J.
I also worry. Yes. So this is 1. That I agree. Only what's worrying me is that you might have 0 in denominator.
Yes, of course. This is a problem we should talk
Yes. Okay.
if something happens here, since the basis we can, there are some bases we can choose, freely choose.
Mhm.
If something have there's some 0 here, we can just for example, the coefficient the same. We can choose say if we say this equals 1 H2.
Mm-hmm.
Just choose the smaller H2.
Then we can just choose
Like half of it, H2 is be the new H2.
But half of it of H2 will be still the same thing.
Okay.
how we fix this.
So suppose that such thing happens. I'm sorry. So why do you have this? So here is just 1, and what's the subscript here?
G.
J. I think you just can get rid of such term. Can you? And then no. So suppose that so what happens here is lambda 1 h1 minus lambda 1 hj. So when we apply to v1, yeah, so it will be 0.
I think there is the one of this J should be 1, I think. Yeah, because when you take V1 here, this two terms should be equal.
Yes.
Yeah, so one of this should be 1.
Yes, I think should be the same. This should be the same as here, right?
Yes.
So h1 and then lambda j h, lambda 1 h1 is here, and then lambda 1 hj, so this one should be 1. And maybe different also order, right? To get not a minus sign, but that's technicalities. But then you just say, okay, you have, suppose you still have, no, but then this is bad because it's just 0 everywhere now.
So
Yeah, yeah,
this
so
is not.
this another. It should be H1.
Yes, so it all boils up to some, right, so once you fix a basis, right, so now you have these vectors. So let's call this as lambda ji. Okay, so you have a bunch of numbers. So maybe you can fix this, but let me just formulate a simple problem. So suppose you have a bunch of vectors, lambda j, right. So j should be, where is my index j here? Here. So lambda j, it's as a vector, is lambda j1, lambda j, so how much r we have them, right? So lambda j is this. So the problem is the following, that there exists polynomial and as vectors, right? We know that as vectors, Lj is not equal to lambda k if j is not equal to k, right? So this is what it means, different weights, right? If the but sum of if j is not equal to k, sum of entries can coincide, of course, but as vectors they're different. Okay. Now the question just from for just usual polynomials in many variables. So there exists a polynomial p in variables x1, x. So how many r? Okay, such that p of well, and they also have some indices, but okay, so at least say p for given j, p of lambda j of this vector. This is clear what it means, right? I just take first entry, plug in instead of first variable, and so on. This is 1, and p of lambda I is 0 for every I not equal to j. So this is just some problem about polynomials. So we just need to generalize Lagrange interpolation formula. Yes. So and it is so then the claim is that you can solve it. Okay. Of course, there is some explicit way how to do that, but maybe not go into technicalities, because we will. So maybe we can discuss it after, just not to spend. So the claim that this problem can be solved, maybe not. So some mistake in this particular explicit, right?
Yes, yesterday we considered when it's 0, but
again forget how we consider.
Okay, so might be 0. Something
yes,
something.
Zero, but if
Something
0,
can be yes.
Yes, if it's 0, we can make some claim that we can drop these things and to find some some solution from for example from V2 to V key, and then we add V1, just make some new polynomial only for V1, since the rest act on V1 is just 0.
Mm. Okay.
And I mean, if the dominant will sometime be 0, and then we can know that
because we can choose a new basis for each AI, and then yeah, so that's lots of freedom to choose basis H.
It should. Yes. Okay. But still, something is what. So what I claim is that this problem has solution. Okay, and you can write it explicitly as in Lagrange interpolation. So okay, you can do.
Yes, we only consider numerator, and we can check this will be correct. That G is not equal to I. This will exactly 0. Right.
This one is 0 because of this terms.
Oh, yes.
Yeah. Yeah, if there's no 0 denominator, this works, of course, but yeah, not sure. Okay, so suppose so your A1 is this P, right? So you take so in this term, so this is just polynomials, no Lie algebras or anything. So your A1 here then is this P of H1, how many of them? N? Okay, let it be N. I had R there, but whatever. This is R on the right hand side. This is P where J is 1, right? For given J, so here J I should take 1. Okay, so okay, we found this A1 and then A2 and so on. Suppose we found them. Yes, okay.
I think I just, when I googled this formula, I found without denominator, it was something like,
Without denominator.
like it was.
So maybe you don't rescale.
It was I minus J and then Hij minus 1 Hij, something like this. So when it's
This is Newton particle.
What is
like the same, I think more like because I didn't get fully what it was written, but something like when I will be equal to J, so we will act on Vj. So how to say that?
But
Like
I'm sorry,
one?
this negative one, it is for what? I think this is for the whole product. So what does it mean? What this inverse stands for? You take inverse of what?
For Hij, as I remember.
And Hij is who are they?
It's just element of H, that's Google page.
Yeah, but you have basis, right, which is actually labeled by one index, right? So far it's not clear what are two indices here.
Yeah, we found the history.
Looks like this Newton polynomial, but it's not exactly is. Looks like. So it's just another polynomial to solve this problem, I think.
Yes. Okay.
Okay. If we suppose we solve this, this problem. And
Yes. So this one I checked, and I actually wrote some formulas. If I try to remember them now, then we'll lose some time. Okay. So that's why I'm not doing that. But this is some exercises in how to generalize Lagrange interpolation. Okay. So yeah. Next argument was so suppose you found this A1.
If we found this, then we prove the first claim of the hit. Right? The
Yes.
thing is we can find some such this happen.
Right.
Since we just try to find A1, and we can find A1, A2. Okay, such this happen.
Yes.
And if this happens, we should prove that for some V, since we know this V should be in M, then it can be it can be decomposed with some
Weight vector.
some weight vector. Yeah, weight vector can be write down. And this weight vector of M of distinct weight. Then we should prove that every vi we should prove every vi is in V. So if this happens, this means it have the same the weight vector in V has the same weight as the weight in M.
Sure. Well.
Here is the submodule V.
Yes.
Here is the vector V.
Yeah. You cannot have any other weights other than in M lambda.
Yes.
That's for sure.
And
Well.
what?
Yeah. If it's some model, you cannot. Yes. Yes. Okay. Yeah. Please continue.
Oh,
How we do that? We just apply the polynomial we just find, and let's just give, for example, V A1 act on V, we get what? We just get V1 since it's submodule. So since this V is also we choose some vector in this V, right? Since this is a submodule, it means it's closed with respect to these things. So
Right.
it means this is in V. Right? So what is this? It's just V1 by the previous
Yes.
things we proved.
Yes.
So it now means V1 V.
Yes.
For any V, I, then you can choose. Then you prove this is correct. Then you prove the things we should prove in problem 1.
Yes.
Yes.
So we're done. Okay. Thank you. Let's move on to number 2. And okay, Prasun, can you do 2? Abner and Valentina can help Prasun. Yeah, I didn't think about this. Yeah, we already somehow actually asked me before the lecture. I'm not sure. I need to recall everything accurately. Then we can discuss. Yes, but what is upper bound in this setting and. It might be true, but this is already easy enough. I mean, yeah. I mean, it might be true. Just
question is
yes.
any lambda to this, there exists an irreducible representation of lambda.
Okay.
So we need to prove this. Now, so we can take the for any x star for any lambda and x star we can take the Varma module of this and I write this. This is the formal module, and this will be like so. We can write it as some so this is our module, and we have a decomposition like this.
This is just for curiosity. This notation from where?
It's just the summation of.
Yeah. I mean, I guess this is from some book, right? Delta. Yes.
This is for
No, I'm just curious who denotes thermal modules. Okay.
okay. So
Uh-huh.
so in problem 1, we had proved that if it has a submodule,
Mm-hmm.
then it can also be represented as it can also have a decomposition,
Yes.
this submodule.
Uh-huh.
So, and this formal module is actually the highest weight representation of this.
Mm-hmm.
So if we so we need to find the maximal submodule of this,
Yes.
and if we quotient this by this maximal
Mm-hmm.
module,
Mm-hmm.
then this is our this
I think it should be the maximal submodule which not contain the singular vector.
Yeah, the highest weight vector.
yeah,
Yes.
proper
Mm-hmm.
proper.
Not just
Proper.
proper,
Yes.
you should more condition that it must not contain the singular vector. That's space. That's the one-dimensional space.
Yeah. What if it's proper, but it contains V lambda, which cannot happen, of course. Right? Well, proper is okay to write here, right? So if it contains,
It's not proper.
it's not proper. On the other hand, if it doesn't contain, it's so proper. So it's to both ways. Yes. So okay.
So if we can find this,
Mm-hmm.
then we can.
Then we
find
solve the problem. Yes.
Yeah.
Uh-huh.
So okay. So let's take sum of all the proper submodule of this.
Okay.
So I can. Okay, so this will be. This is the sum of all proper submodule.
Okay. But we need to prove that, right?
Yeah. Okay, so let's just represent this. I'm just writing it like this now. This should be inside. It should be inside.
Mm-hmm. So you need to check that it is proper, so which is equivalent, as we discussed, that the highest weight vector is not in the sum,
Yeah.
right? So
Okay, so
okay, let me maybe help you out here a little bit. So you take highest weight vector. Yeah, thank you. So you have v lambda, right, which is the highest weight vector. Yeah, okay, I'm more used to this, but this is your delta lambda, right?
yeah.
So you would like to see that v lambda is not in the sum of what's this is how you denote it?
This is the sum of all proper.
Sum of all proper submodules U, I don't know, right? But let me take, so it means that V lambda is not sum of U1 plus U2 plus so on plus UK for some elements in proper submodules,
Yeah.
right? So this is in U1, which is like big U. It's a proper submodule. It's another proper submodule, and so on. Right? So now you take this and decompose each UI in a sum of weight vectors, right? This is just an element in U1, and U1, each proper submodule by problem 1 can be decomposed into weight vectors, into weight submodules, right? By problem 1, UI is a direct sum of UI mu, but because it's proper, it's strictly less, right? So therefore, UI is decomposed as UI I mu1 plus UI mu2 and so on, UI mu k, right? Where each mu I here is strictly less than lambda, and this is for each I. This is for each I from here. So in this sum is actually sum of weight vectors, and each weight is of this vector is strictly less than lambda, right? So therefore, you cannot never get v lambda out of that because weight of v lambda is exactly lambda. Okay, so therefore v lambda is not inside this sum. Okay, so now how to proceed? So that's how you apply problem 1, right? To actually see this, right? Mm-hmm.
So it means that.
So you take a sum, and it's proper. We just proved that.
So. I think for any, this will be non-zero. This
Okay, yes.
and
So therefore, at least we have non-single a singular vector, and it's proper and maximal, right?
yeah.
Unique.
Well, unique, it's we proved, yeah, but we don't need it here, right?
So I think then it is irreducible.
Yes, but why is it maximal? So since it's maximal, it's this one is irreducible and of highest weight lambda because v lambda still in there, right? We didn't quotient by it. But why it's the sum is maximal? So what does it mean maximal?
It means that the vectors from
Yeah, so you have that every proper submodule U is inside sum over U, right? So actually, if you take any submodule, that it will be inside. So it's maximal. So this sum is maximal with respect to this to inclusion. It's just by construction it's maximal.
okay. So
Right.
um, can you explain this once again?
Yeah. So what does it mean for if you have a module? I don't know. V.
Yeah.
What does it mean that it is maximal? It means that if we have some other proper module, I don't know, W, it's if you have situation like that, then either W is V or W is M lambda, right? Another way to say that is that any proper, yes. So, but suppose that you have W, so V is our sum, right? U. Very well. So we would like to see if we found some W like that. It's either M lambda or V, right? So if W is not proper, then it's M lambda, right? And we're done. If W is proper, then it is actually one of the terms here, because we sum over all proper submodules, right? So if W is proper, then it's one of the terms here, and therefore W is inside V. So we have two ways inclusion, V in W and W inside V. So W equals to V. So we have, if it's not M lambda, then it's V. So therefore V by definition is maximal.
Okay.
So it's maximal, highest weight here. It's so we're done. It's irreducible representation of highest weight over lambda.
Okay.
Yeah. Okay. Thank you very much. Yes.
So can you please kind of re-summarize how we did the second problem? I tried yesterday and I couldn't make any progress.
Yeah. So again, the whole idea is that construct L lambda out of M lambda. How to do that? We do that if we find some proper maximal submodule in M lambda. Is that clear?
Yeah, that was clear, but I didn't know how to find the maximum submodule.
The idea is very simple. You just take all proper and take sum of them.
Okay.
So all proper are already contained in him. So that's how we do maximality.
Yes.
Okay. And then we just need to check that if you take sum of all of them, it's still proper.
Okay.
Because otherwise, if you quotient by it, you kill everything and you don't get highest weight representation, right?
Okay.
Then we check that it is actually proper.
Okay.
So we check that V lambda is not inside this sum.
Okay.
And how we do that, we say that every sum, every element in here is actually a linear combination of weight vectors with weights strictly less than lambda. So you never get V lambda then. So that's how we did it.
Okay. Okay. Thank you.
Mm-hmm.
Well,
It's not
maybe
it.
we
Sanchit, you got something?
Yes,
Okay.
but I also didn't get the full answer to the end.
Okay, let's see.
So, in the Telegram chat yesterday,
Mhm.
you said that the Casimir is an element xi.
And more importantly, I said that some number of lectures ago.
Okay. Okay.
Okay.
Okay, so,
So
this
that's a good Telegram chat actually helps refreshing. Yes.
yes, so
Uh-huh.
this is xi, and they are dual bases.
Uh-huh.
And okay, if I have some Lie algebra, I
Mhm.
can consider that it is of some E, F, and H. Make the basis here. Okay, so and this you wrote it below the question that.
So it is G. Ah, okay. Mhm.
So you wrote below the question that we have the these are bases with respect to the killing form such that E alpha F alpha is equal to 1.
Okay.
Okay, and then HI is also formed in orthonormal basis.
Yes.
Okay, so if I want to write this
Mhm.
as a combination of E, F, and H, so I have just this thing. And because HI also is like
Square
HI,
Mhm.
like J then
Delta IJ. Yes.
So HI square 1R. Okay.
So H. So but you need. So your basis is what? Your basis is this one, F alpha. Alpha runs over
All the positive roots.
positive roots. Then E alpha. Alpha also runs over positive roots. And H1 HR. So this is your basis
Yes.
that you now for each element in here, you should find dual.
Yes, yes.
So you claim that the dual for E alpha, say, is
F alpha.
F alpha.
Yes.
Why is that true?
It comes from the Cartan killing matrix. I think we have studied this before. Not Cartan, killing matrix.
Yeah, but what should we check? We should check that this is 1,
Yes.
but this is given.
Yes, exactly.
But also you should check that E alpha with
F
anything
beta
from here
is
is 0.
yes, that's something I was thinking how to do. Like, let's say if I just try to take even F beta, how will I get a 0? Or E alpha with H, how will it be 0? That's something I was trying to do.
So again, this is again actually what we proved some number of lectures ago, that killing form of this or any invariant form actually is 0.
Okay.
It's just because you take adjoint action
Yes.
on this, it will give you alpha.
Yes.
But because of invariance of the form, you can transmit it to here, and it gives you another scalar, beta, which is they are not equal, so therefore this should be 0. So that's how we proved that.
Okay.
So this actually gives you all these zeros,
Okay.
because H's live in G0.
Okay. Okay. So yeah, this is the form of C, and
Yes.
then we have to prove that if C acts on, I'm writing it by lambda, the highest highest weight vector,
Okay.
lambda, then this has the eigenvalue of the form of lambda, comma, lambda plus 2 rho, and rho is given by half r plus alpha.
Okay.
Okay, so, well, it's also something that I was trying to do, that I can write E alpha, F alpha as, okay, first of all, we know that E alpha will kill this because it's the highest weight vector, okay? So, where did I write this thing? So this one will kill this, so we
Yes.
don't get anything corresponding to that, then we have this. So I can write E alpha, F alpha as F alpha, E alpha plus E alpha, F alpha,
Yes.
which is equal to 2H alpha. I think there's relations between the.
What? Okay. What is H alpha though?
H alpha is different.
Oh, this H alpha is different. I think it's this.
Not really,
Not
because so what is H capital? Okay, let me write it here. What is true is that E alpha with F alpha is E alpha with F alpha killing form times H capital alpha.
Okay.
So this one is 1. So E alpha with F alpha is actually capital H alpha in this case.
Okay.
So when we were writing before E alpha F alpha equals H alpha, we had different normalization here.
Okay.
This equaled 2 over alpha alpha
Oh
before.
yes.
So
Okay.
so this was for different normalization for E alpha and F alpha.
Okay. Okay. So it's corresponding.
So
to the same.
we have this. So E alpha F alpha is H capital alpha.
Okay.
Maybe it resolves the problem with,
I know how. No,
Okay.
definitely not.
yeah.
Then we have okay. Now the C is after operating on lambda.
Yes,
This one will kill,
yes.
and this part when I write this no.
This one will kill. Yes,
This I can write it like this part again. E alpha will kill, so I
Yes.
have this.
so it's just H alpha
alpha plus
epsilon lambda, right?
R, yes. Chi square, this acting on lambda.
Yes. Mm-hmm.
Okay, but this will just give me a lambda, H alpha on lambda.
What is
in
so?
a
This
product-
should be a number. Lambda so far is a vector. So it should be
It's
more
the
specific.
Weight of this highest weight vector, which is lambda.
But weight of highest, it's not SL2, right? It's still a vector.
Okay, so it's how do I write
Use
it?
the definition of the big H.
What is H alpha acting on lambda? Just what's the definition of being a weight?
It's it's itself is a vector with the
No. So if my V is a weight vector of weight lambda, it means that H for any H from H Gothic is lambda of HV. So this is just
Okay.
definition.
okay.
So this should be lambda of H alpha.
Okay.
This is already a number, and this is good.
Oh
Yes?
yes, yes.
So this is what this gives you, this term, right? Plus something.
Plus now this HI is this thing.
Mm-hmm.
So okay. I think we have H alpha, something like this here.
So HI is not H alpha, though. HI is some
This term is the lambda.
H alpha I should notice are not orthogonal with respect to killing form, though.
Yeah.
Alpha, yes.
This term will be.
Otherwise we would have only orthogonal roots in any root system.
This term should be the square of lambda, the length of lambda,
Yes.
because it's a basis.
It's
But so far you can use this also this. Yes. Lambda of HI squared.
oh yeah.
Mm-hmm.
And then this whole thing with the, of course we still have a lambda here.
Yes. So we need this number, maybe sum over alpha
Oh yes, sorry.
here.
And there
Uh,
I used to want to.
Yes. So we need this number to be lambda plus rho, right?
Yes, exactly. I think it's 2 row.
Two row. Yes. By the way, why do you have 2 here? I don't think you have 2.
Ah, yeah. I was before writing.
Yes. Okay. So let's deal with this term. So this is by definition just lambda alpha,
Yes,
right? Sum over all alphas.
yes, yes.
So this thing is
Oh,
lambda
it's
alpha.
sum over all the alphas, yes.
Sum over all alphas. So this is exactly lambda to rho.
Okay. Oh,
The only thing is to see that this thing is lambda lambda.
Okay. Just 1 minute, let me think about this. It's lambda with, of course, h alpha is always sum over all the alphas, which is 2 rho. Okay, I think 2 rho is written. Yes, yes, exactly.
Yeah, so the first term is exactly lambda to rho.
Yes.
And the second one, we would like it to see that this is lambda lambda. Why it is like that?
I can.
So yeah, maybe
I
I'll
can explain
can.
this.
Yeah, thank you.
By using
Thank you very
the
much.
physics
Notation. Okay, physics
Yes, and
notation.
what is this? This is like you always like to write, and you can expand it in another representation by using this I.
Yes.
This thing or thing, and this part is exactly what it is. Yes. So,
Yes, yes.
so this term is the this, or you can write it like this.
Okay.
Then this
It
is
makes
nonsense.
sense. Yes.
Mm-hmm.
And actually, another thing is you should prove this. You just calculate what number it should be when this Casimir element acts on the highest with the singular vector, but you don't say that why it must be a constant in the whole representation space.
Yes.
Okay, yes.
And why is it? Because any vector from our representation representation space, irreducible representation space, it's you can always present it like some f acts on the highest weight the singular vector, and then you act this, and this commute with everything, so
Yes.
it's become that constant.
Okay. Okay. So I didn't prove the part that it is actually a Casimir and that it's.
No, we proved that. This just should be said that since it commutes, since it's Casimir, it commutes. How to compute its action on any element?
Okay.
It's just it commutes with this, hits V0, gives this number that we computed,
Okay.
which you can factor out.
Okay.
Yeah, and
Yes.
another thing is that the first problem is you need to prove that any Casimir you can rewrite it to be this form, but I think you didn't prove it.
No, we
It just
It
means
is
it didn't depend on the choice of basis.
yes,
Yeah.
that we proved.
Okay.
Yes. No, we didn't prove it today, but we proved that I believe during the lecture on Casimir. Yeah, it was a long time ago, so people don't remember.
We prove it. Yes.
That's very good. All right, number 3 is done. Let's do number 4. Okay, we have a number of people who did 4. So we have you have to choose between Christina, Abner, and Valentina. No, who wants?
I'm okay.
Okay, so
Yeah, I'm wrong, but I'm not sure about my contradiction in there.
no.
Also, don't know how to do it in another way.
So if you thought about this problem, that the best place for you to be when you're discussing is at the desk, because then you understand everything much better. Right?
Okay, so the problem was about to prove that any irreducible, irreducible reduced system in any
Mhm.
reducible reduced system exists one and unique, and yeah, that's all. Root of maximum height.
Mhm.
Okay, so I don't know how to write. Okay, it exists. Okay, so there's two parts: existence and uniqueness. It should be, yeah. So
Mhm.
with existence. With existence, I think it's pretty simple. We just need to say that it's irreducible. So it should have at least one positive root. Yeah?
Yes.
Okay, so.
I mean, you have root system,
Yeah.
so it should
Okay,
have at least
okay,
one
okay.
root.
Yeah.
Yes.
that's
Okay.
right,
Yes.
even
Yes.
Even it's not irreducible.
Uh-huh.
Okay, so it's what else? Okay. we
And you have
this-
finite number of roots,
Yeah.
and each has height.
Yeah.
So
Yeah.
therefore-
So at least one should be with.
Maximum height.
Yeah, with maximum.
Yes.
Okay, that's
Yes.
all.
That's clear.
So existence is
Uh-huh.
one. I
Mhm.
think. Okay, with uniqueness. Okay, yeah, we will construct a contradiction, and we will
Mhm.
assume that we have alpha. Okay, let's already exposed
Mhm.
through simple roots.
Mhm.
It will be something like an I, alpha I, and the same for beta max. It will be just another coefficients. I, alpha I. Okay, so, and also they are not equal.
Mhm.
So at least one I, okay, let me be J. At least one J should be like this, that's n J, not equal J. Okay, so and then for convenience, we will change J to I, just to say that's like we have alpha with coefficient, with such coefficient ni that's bigger here than this mi.
Sorry, say it again. I'm just I just
Yeah, okay,
missed.
maybe. Okay, so they're not equal.
Yes.
So at least should be one I coefficient. Okay, let it be I. Oi.
Okay. So you want this coefficient to be I, so let's
Yeah.
change it to
Uh-huh.
I. Okay.
Okay, coefficient I such that n
Mhm.
mi not equal mi.
Okay.
So it exists one simple root, alpha I, at least one simple root, such that coefficient in alpha max is bigger, for example, let it be bigger
Mhm.
than coefficient in beta max.
Yes.
Okay, for example,
Mhm.
let it be like this.
Mhm.
Okay, what next? Okay, so it's actually time to construct a contradiction, and okay, let it be like this. We will see. We will look at reflection. Say as alpha I. Okay, I will recall. Let's look.
Mhm.
Okay, so we know about reflection that it preserves height or it will decrease height. Yeah, is it true? I think according to formula.
Okay.
Reflection. So what's it?
Reflection, like when reflection acts on root, it will preserve height of this root or will decrease height. Yes?
No
the
height.
Height.
Of course,
Not-
because this is the maximum, you cannot go higher.
Oh.
You just can be lower
Yeah,
or
okay, yeah.
equal, right?
But
I mean, if you have something in the was negative wave chamber, and they reflect it, and it becomes like by the longest wave group element. You get to the C+, so its height actually increased.
But
So
okay,
the statement is
nowadays,
not.
yeah, we have already, like, okay, I will act reflection, I will reflect, no. I will use reflection acting on maximal, alpha max and beta max. So it cannot be higher.
Okay. So actually, yes. So just because you don't have higher, bigger height, then of course you cannot. Yes.
Yeah. So and now this is time to construct contradiction. The first thing it will be like, okay, we can reflect alpha max to something, and including we can reflect alpha max. We can construct a sequence of reflections that will go from alpha max to beta max. Yeah.
Okay.
Yeah, and if they both with the same height, it means that this sequence should preserve height on every step.
Mm-hmm.
So I can write it like this. For example, sequence.
No, this I don't think sequence should preserve height on every step.
But it's sequence of reflections.
Yes, but
Yeah, but like when we go from this to this, the height in the end the same.
yes, but I don't think it's true that the reflection cannot increase height. So
yeah,
think of SL2, right? Where height equals.
It acts on the highest vector.
Yeah,
Highest root.
No, but not only on the highest. She says like a sequence of reflections.
yeah, like we should go from this.
So you apply first one, you're already not in the highest.
Yes.
And then you can increase.
Oh yes.
Then you can go back.
Yeah,
and
then
so
we
you can go back and
okay,
forth.
Yeah, that's I didn't think. Okay, that was the problem of improvement, because I was not sure that this is fully true.
Yeah, I don't think it's true. So just think of SL2, right?
Mm-hmm.
So you have your highest weight,
Yeah,
and
yeah,
you
and
have
in
something
this
below zero, right? If you up, of course, height equals height on a board, right? So if you reflect this, apply simple. There is only one simple reflection, and then it goes here. The height actually increased.
Yeah,
So
but in
not
this
true.
case, height cannot increase because the height of these things is the same.
Right, but you're saying it's a sequence of reflections. You and you say on each step, you should the height should be the same.
Yeah, okay. Okay, maybe okay. I will say the end, and then maybe there's some way to change it from sequence to just one step. I mean, no, actually no. Okay, so the second part it was about like, okay, we will construct a sequence that's will go from alpha max to beta max, and the second thing is that if you will reflect every time, so let's start with one or I, it will be I. So it will 100% decrease. Yeah, decrease height.
Yes.
So on simple rule, when we will act on simple rule, yeah.
So this is I is the same, right?
Mm-hmm.
So this is just negative alpha I, right?
Yeah.
So yeah, sure.
Yeah. So we will 100% will decrease height of simple root.
Yes.
But our maximal alpha consists of all that simple roots. So it means that we will never get this sequence that will on every step will preserve height. Because in at least on one step it will decrease.
Yeah, but maybe the other one can.
But
The other alphas.
yeah, maybe. But
Yeah.
here assumed that this sequence consists of all steps that preserve height on every step.
Mhm.
So that was contradiction. But okay, yeah, you say that it can not preserve
Yeah.
on
Okay.
every step. So that's not true.
Yeah. Okay. But yeah, nice try anyway. So, but you never used representation theory.
Yeah.
So that was that was the problem for after representation theory lecture, right?
Mm-hmm.
You tried to solve it using
My
only root systems themselves, right?